Welcome back. Welcome back. We have a really fun question today to deal with. How the relativistic regime is actually pretty fascinating to deal with, considering what we learned back in chapter 10 with the retardant formulations for the potentials and the fields. Let's just dive on in. So the statement reads: in system S0, a static uniform line charge lambda coincides with the z-axis. Part A. Write the electric field E0 in Cartesian coordinates for the point x0, y0, z0. Part B. Find the electric field in S which moves with speed v in the x direction with respect to S0. The field is still in terms of x0, y0, z0. Express it instead in terms of the coordinates x, y, z in S. Finally, write E in terms of the vector S from the present location of the wire and the angle theta between x and between S and x hat. Does the field point away from the instantaneous location of the wire, like the field of the uniformly moving point charge? All right, fair questions. Let's see what we got. All right, so to start off, we know that the field for part A, that the electric field resembles that of the wire. Hence, we know that E, if we use Gauss's law, turns really easy. We got lambda over 2 pi epsilon naught, S hat over S. But if we break S hat down into S and magnitude vectors, then we could quickly see that we get lambda over 2 pi epsilon naught, S vector S squared. Okay, here, again, since we're on the z-axis, we don't need to worry about the z part of that, so we just get the lambda over 2 pi epsilon naught, x hat, x naught x hat plus y naught y hat, and then of course the distance squared is x naught squared plus y naught squared. Cool. Now let's go back to how the fields transform, and we know that ex bar is equal to ex, so nothing transforms there. Again, x direction, so only take account. Ez is equal to gamma Ez, but of course the Ez component here was 0 since the line was on it. That being said, we have E bar y is equal to gamma E y, so plug in the y component for that. What do we see about gamma? Well, clearly then the gamma direction only affects the y, the gamma only affects the y. So what we need to do is the inverse Lorentz transformation, where we see that we have x naught is equal to gamma x plus vt, but then we also know here in this case that y naught is equal to y. Thus, if we want to find the total bar field for the other system, we have lambda over 2 pi epsilon naught. We were able to transform the x naught component to the x and t, x, v, and t for the other coordinate system, so s bar to s. So we do that for y as well. So we get y naught goes to y, and then in the numerator we have to be careful, in the denominator we have to be careful, because we have to square both the gamma term and the x plus vt term. So all of this has to be squared. And normally we want to get rid of that gamma, plop it out. So we do that, but in doing so we have to force a factor, so we have to put a gamma squared under the y term. And thus we see that we have a gamma in the numerator that cancels with one factor of this gamma squared. Hence we just get 1 over gamma and drop all the gammas that were on the x and y hats. So with that, now let's go see what else is left to do. So what this form tells us is that S, being the vector, is x plus vt in the x hat plus y hat. And so if we write this down into the angles, then we see that y is equal to s sine theta. So in the in that denominator that we have, we can kind of tidy up what we need to as far as getting rid of the gammas, settling things down. You see here, once we distribute the y in here, we get y squared by itself minus the y squared with the v over c. And then, of course, if we do that, we see that this term here, without the minus sign, gives us the s squared that we're looking for. But the y squared on the v squared c squared just gives us the s sine term. That's what we need to square. But in doing so and squaring it, what we see is that we can factor out the s squared. And so we're left with E bar is equal to lambda over 2 pi epsilon naught times 1 minus v squared over c squared divided by the s vector, s vector magnitude squared, and then this Griffiths term with the sign in it. Why does this matter? Well, quite frankly, this looks like something we saw in the relativistic, or excuse me, in the non-relativistic regime, but using the retardation regime. Here we see that if we put the gamma factor in the numerator, that denominator stays the same, the bracket anyways. We could take a factor of that s squared, put it up with the s vector to make the s hat, and so after we simplify down and form match, this is reminiscent of the equation 10.75. So yes, the field does point away from the present location of the wire. But again, the fact that the special relativity and relativity regime gives us the same thing that we saw when having to deal with the retarded positions, this is a fascinating thing to deal with, and probably a much cleaner way to deal with it, because as we saw, finding TR turned out to be very difficult in a lot of situations. So this just makes light of that, and it's a wonderful, wonderful way to view it. That being said, we get more situations like this more often than we think, so having this in our toolbox is definitely worth it. So that being said, I'll see you at the next one.